gentlemen, class recording has started. So, on Thursday of last week, we did our introduction to falling objects and the acceleration caused by gravity. And that started off with this picture. And I asked you to take a look at this picture, and then based on the individual pictures themselves, and then the two pictures in comparison to one another, what can you tell me about this motion? And we talked about that because those objects keep getting farther and farther apart in each picture, that would be accelerated motion. And because they stay with each other as they go along, we can say that the acceleration for both of those objects is the same. And you're real close to the microphone. And we said that that is the case when gravity is affecting the motion of an object, because gravity will accelerate all objects at the same rate. And we talked about the idea that here on Earth, that rate is 9.81 meters per second squared. And we did some examples to say, okay, what is something that experiences a 9.81 meters per second squared acceleration look like? How does that apply to the motion, etc., etc.? But we said that sometimes we don't see that gravity is affecting all objects the same way, because we said that that constant acceleration for all objects only applies when gravity is affecting those objects and nothing else. That if there are other effects, other outside influences that affect the motion of those objects, we may not see that constant acceleration being the same, but if we can isolate where it's just gravity, we would see that same acceleration. Okay. Good there? And then we talked about this. I don't know if we actually talked about this picture or not. Did you guys look at this picture? Okay. This picture illustrates that idea that in class we took, and I threw the ball up in the air and then I caught it again. Right? We talked about that for a long time, yes? Okay. That gravity is affecting the motion of that object the whole time, and it causes the acceleration to be the same for that object the entire time. But what that does to the motion of the object depends on what the object is doing. So gravity can cause an object to slow down or speed up any kind of acceleration at the same rate. So if we talk specifically about the up trip, okay, and we talked about this on Thursday, we may not have shown you this slide, but we definitely talked about these things. If we talk about that object on its trip from my hand up to the top of its motion, we throw it up in the air. It has a velocity in the upward direction because that's the way it's moving. So we could say that if we call that the positive direction, it would have a positive velocity. But because gravity is pulling it in the downward direction, it has a negative acceleration. So we talked about the idea that in the case of the upwards trip, acceleration and velocity are in different directions. And when that's the case, that causes the object to slow down, right? If it has velocity and acceleration with different signs, it causes that object to slow down. Good there? But on the down trip, now that object is moving in the downward direction, so it has a negative velocity, but acceleration, gravity is still pulling it in the downward direction. So now it's moving in the same direction that gravity is pulling it. If something's already moving in a certain direction and we pull it in that direction, what's going to happen to it? If something's already moving one way and then we continue to pull it in that direction, physically what's going to happen to that object? It's going to go faster, right? So we have acceleration and velocity in the same direction on the down trip, and therefore that object will speed up. But the acceleration is constant the entire time. The velocity changes, but the acceleration is constant. Gravity is always pulling it downwards. Sometimes that causes the object to slow down. Sometimes it causes the object to speed up. but it's always being pulled in a downward direction. Good there? And then we talked about the idea that first we looked at this graph, right? And I had you guys sketch some graphs about what they're supposed to look like. And this is the position graph, the blue one, right? Nice and symmetrical around the top. But then the velocity graph shows a decrease in speed up until that point, and then an increase in speed, but in the negative direction. If we looked at the object a certain time before it got to the top and a certain time after it got to the top, what we would see is that that object is moving just as fast, but in the opposite direction, because gravity causes it to slow down and speed up at the same rate. Sometimes that causes a slowing down effect, sometimes a speeding up effect. Okay. Good there? All right. We are going to start off today on page 98 of your book, on page 98 of the book. Oh. And on page 98 of the book is conceptual example 3.11. Now, if you are actually looking at the book right now, there is a little explanation of the answer and everything like that, but try not to read that right now, and let's just talk about what's going on here.
I will beat the as soon as I can.
Okay. So,
All right.
yeah.
Are you recording stuff?
Yeah. So,
Sure.
it's all right. You're there for posterity now. So. All right. So on page 98, let's put that up here. So page 98. Okay. Does the separation change? So it says you're standing on top of a bridge and you have two rocks. So you drop these rocks, but not at the same time. You drop one first, you wait a little while, and you drop the second one. You wait until that rock has fallen 4 meters, the first rock. So you got red that you drop, okay? And after it has gone 4 meters, then you drop blue. So what it's saying, what it wants you to know is, after you drop the second rock, after you drop blue, will they stay 4 meters apart as they fall towards the water? Will they end up more than 4 meters apart? Or will blue catch up to red and they end up less than 4 meters apart? Okay. So they either stay the same 4 meters as they fall to the ground, they get farther apart, or they get closer together. Okay. Discuss. While you guys are discussing, I'm going to draw a picture up here on the board to talk about what we're going to talk about. Okay? Discuss. Go.
If they haven't dropped that one, so it's already, it's gonna be going faster. I don't know. I think it could be the same.
Oh, they're so cute. I have one.
It's so when it first drops, doesn't even slow down, so it's obviously. Yeah, but it's
It's pretty much like suction.
takes just as long for it to be at rest. Yeah, but the first one that drops on the rest, it's already 4 or 5. Drop another one. You wait 4 meters, not 4 seconds.
I just like
Yeah,
that.
4.
And my ears, I don't have any. But my sister's deaf in 1 ear, so she got all the ear problems. Like she gets infections.
No, what I'm saying is that the red one already is going faster than the blue one. The blue one's gonna spin.
Okay. So let's talk. All right. So, I have drawn two pictures that illustrate different properties of the motion of these two objects. Graph up at the top. What is the graph up at the top representing? Those are velocity graphs up at the top, okay? Because, right? Joe, what's happening to the velocity of these objects as they start? It's increasing, right? And how is it increasing, Joe? Nice constant rate, right? Nice constant acceleration. Red starts when time is equal to 0, but blue doesn't start for a couple seconds afterwards, all right? All right, so red starts right away and it starts accelerating right at the very beginning, but blue doesn't start until 4 seconds after, or not 4 seconds, but a certain time after, right? That's the point when blue starts, but red's already moving quickly, right? Red will continue to increase in speed, blue will increase in speed as well, okay? What would we say about these two lines? They're parallel lines, okay? Because on this graph, the velocity graph, what does the slope tell us? Acceleration. And the acceleration of both objects is the same. But does that tell us where they are? No. For that, we got to come down here, right? Okay? Down here, these are position graphs. How do I know that they're position graphs? Well, I drew them, but I drew them. That's how I know they're position graphs. But how would you know? Because they have what?
Curve.
They have a curve, right? And we said that position graphs for objects that are accelerating are curved, right? Because the slope keeps changing. So red starts off and faster, 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 right? But blue doesn't start until here. This yellow line that I just drew, what does that represent? What distance does that represent?
4 meters.
That represents 4 meters, okay? Because that's how far apart they are when blue starts, right? So now, let's take this line and move it over a little bit. By moving that black line over, right, I'm increasing what?
The time.
The time, right? Because I moved it along the x-axis, yes? And now, if I draw this yellow line in right here, what do you see about the length of that yellow line versus the length of the first yellow line? Meaning, what happened to how far apart these objects were? They keep getting farther apart as they fall. Because red's already going pretty fast when blue starts, right? But it keeps getting faster and faster and faster, just like somebody said over here in the corner. So, all right. Are we good there? Good with that example? Okay. All right. Next, let's go to, oh, not that. Let's go to page 109. Page 109. And on page 109, let's look at question number 124. Question number 124. So question number 124 says, a carpenter, says a carpenter on the roof of a building accidentally drops her hammer. As the hammer falls, it passes 2 windows of equal height as shown in figure 3.35. So as it falls, right, there's the hammer, it's going down, it falls past window 1, it falls past window 2. So part A says, is the increase in speed of the hammer as it drops past window 1 greater than, less than, or equal to the increase in speed as it drops past window 2? And then part B says choose the best explanation among the following. And there are 3 choices down here at the bottom. So, discuss. Is the increase in speed greater Window 1 or greater than window 2. Ready? Go. Talk.
It was always increasing to Instagram.
I think so. Yeah, because you said we drop. Remember you said you drop from the tower?
Oh, she gets more velocity.
Then you kill someone or whatever.
That's
So
what-
that they weren't saying kill.
That's true.
Well, it seems like kind of just.
All right.
Yeah, because like.
So let's discuss.
Yeah. I don't.
The key to this question lies in the part that I highlighted, right? So what is this question asking you about? This question is asking you about the acceleration. It is asking you about the increase in speed. What do we know about the acceleration of this object the entire way down? The acceleration isn't increasing, right? What's increasing? The velocity, the speed is increasing, but what do we know about the acceleration? It's the same because what's causing it? Gravity. So the answer to this question is B. The constant acceleration means that the hammer speeds up the same amount for each window. If we look at how much faster it goes from here to here than from here to here, it would increase in speed the same amount because it has a constant acceleration. Good there?
Wait,
Good, Jeff.
so you drop something, it has a constant acceleration but a different velocity.
Correct, because the acceleration is the change, right? So here, Joe, let's do this. Nope, not there. Here. Not that. This. All right, so on that same page, 109, question number 125, this graph right here represents the velocity of that hammer as it's dropped. Okay? So what do you see about the velocity of that hammer as it continues to fall?
It's increasing.
It's increasing, right? But what isn't changing about this graph?
The slope.
The slope, or the rate of increase. Does that make sense?
Yeah.
You know, it keeps getting faster, but it keeps getting faster by the same amount each second. Okay? So this question says, if you look, it says that, notice that the times when the hammer passes the two windows are indicated by the shaded areas. So this is where it's passing window 1, this is where it's passing window 2. Does that make sense? First, which takes longer, passing window 1 or passing window 2? Passing window 1, right? Does that make sense? Why? It has a slower velocity, right? It told us that the windows were the same distance, the same length, but if it's going slower in 1 than it is in 2, it should take a longer time. And that's what the graph is showing us. Okay? The last part here is asking us about the area of the shaded region. So it's asking about these blue parts that are here. Last week, we talked about that on a velocity versus time graph, the area under the curve, that's the area between the x-axis and the graph itself, the parts that are shaded right there. It told us something. Do we remember what it told us? The area between the x-axis, it tells us the displacement of the object during that time. So we've already established that it's a shorter time that it takes the hammer to go past window 2 than it is to go past window 1. But if we looked at the area of these shapes here, what should we see about those areas? They should be the same. Why? Because what did it tell you about those windows in the last problem? How big are they? They're the same size. So even though it takes a shorter time, right, it's going faster. Even though this shape is wide but not very tall, and this shape is narrow but much taller, if we looked at the area of those blue shades, they should be the same. Okay? Good there? Okay. Next thing I want to do for you is do a couple of demonstrations. So the first demonstration is called the effect of free fall on friction. All right. Here in my hand, I have two bar magnets, okay? North pole, south pole, yes? Okay? And if I hold them together, they stick together, right? North pole attracts south pole attracts north pole, opposites attract, all that good stuff, yes? Okay? All right. Let's see. Oh, I didn't save it. Boo. Anyway. All right. If I take these two magnets and put them on this book, like this, okay? What do you not see now? What do they not do? They don't come together, right? Is that because they're not attracting each other anymore? No. They still attract each other, but is their mutual attraction now the only thing that's affecting them? Now they also have to deal with what as they sit on this book? The friction here on the book, right? So the friction between the book and the magnets is preventing the attractive forces of the two magnets from pulling them together. Okay? Good there? All right. So I'm going to take this book to a high place. So, here's what I'm going to do. I'm going to drop this book and the magnets on top of it. Okay? You might be able to see it on the way down, but all of you should be able to hear what happens almost immediately after I drop it. Okay? All right, are we ready? Okay. Pay attention. Almost immediately after I dropped it, what did you hear? Clink, right? Because once I let go of that book, what starts happening to it? It starts accelerating due to what? Gravity, right? Then, what starts happening to those magnets? The book starts accelerating due to gravity, right? So it starts falling. What do the magnets do then? They start falling too, right? What rate? Same rate, 9.81 meters per second squared. Because I take my hand away from the book, friction gets caused because gravity is pulling that object down into another object, right, and causing the friction between the surfaces. But if I let the book go, now the book and the magnets fall at the nice same rate. Is there any friction between the magnets and the book then? Nope. And if there's no friction between the magnets and the book, what do the magnets do? They'll attract each other, right? And they'll come together and they'll stick together. Okay. Good there? All right. We're good. Just want you to know the next demonstration, and Alex too. You guys are kind of in the splash zone right there, all right? Just so you know. It's gonna get wet in this area, so if you want to move, might be a good idea. So, it's like SeaWorld. All right. Next demonstration. involves this water bottle. Okay? So I'm going to take this water bottle. And I'm going to fill it up with water. And before school this morning, I put a hole in this water bottle so the water comes out of it like that. Okay? Alright, good there? And apparently when I dropped it before, I put a hole in the bottom because it's leaking on the bottom as well. Okay? So, I'm going to let the bottle go. Alright? Now, before it hits the ground, it's probably going to make a big splash when it hits the ground, right? Or you might want to move your backpack too. Just throwing that out there. Just, you know. Yeah. But, the moment I let it go, what should we see happen here based on our experience from the last demonstration?
No water should come out.
No water should come out, right? Because right now, what's happening? Why is the water coming out?
Gravity.
Gravity is pulling on what?
The bottle and then it's like,
No, but that pulls on each molecule. That's why water sticks together.
That's true. But that would, but if there
Gravity
was,
supports this pushing
right,
through.
okay, that in this case here, gravity is pulling on this water and causing it to fall downward. Is gravity pulling on the bottle? Yeah. But what else is affecting the bottle?
your hand.
Me, right? So the bottle can't fall under the influence of gravity. But water doesn't have that influence, so it falls, right? But when I let the bottle go, what's going to start happening? What's going to start happening to the bottle?
It's gonna fall.
It's going to fall. How fast compared to the water?
Faster.
Just as fast.
Because why? They're both being affected by what? Gravity. And gravity affects all objects the same, right? All right, here we go. Ready? 3, 2, 1. Did we see it on the way down at least?
Yeah.
Okay. Apparently earlier somebody took a video while I was doing it. Not apparently, somebody did take a video while I was doing it. And they're supposed to send it to me later today, but we'll see if that happens or not. So, okay. But in that case, right, now we have the two objects, right, the water and the bottle, both falling at the same rate. So now the water doesn't come out, not because gravity isn't affecting it, but because gravity is affecting both of those things at the same rate. Good there?
Yeah.
Let's try it now.
Go for it.
All right. You can go. You can back sit down.
Alright. Is the mic still on?
Sit. All right. To wrap it up here today, we are going to go to page 99. Page 99 of your book. And on page 99, there's a problem called doing the cannonball. Is that what it's called?
Yep.
Do the cannonball. Now, this problem here on page 99 is a guided example problem. Meaning, if you're paying attention, you can follow right along because it does the problem for us. But I want to make sure that we understand where they get all of these things from, so let's go through the process. So it says, a boy steps off the end of a 3-meter-high diving board and drops to the water below. So part A says, how much time does it take for him to reach the water? What is part A asking us for? Part A is asking us for time, right? And in the previous portion of this this unit, when we were talking about trying to find time, how did we do that? If we wanted to know the time of something, where would we go? Kinematic equation, right? But we said that kinematic equation only applies in certain circumstances. Do you remember the conditions that had to be met in order for us to use kinematic equations? Kinematic equations only apply if
It's constant.
constant what? Constant acceleration. All right? Constant acceleration. Is this an example of constant acceleration? Yeah, because what's causing the kid to fall down to the water? Gravity. So we can use kinematic equations to help us solve this because objects under the influence of gravity have a constant acceleration. With that being said, let's start going through the process. We know what we want to find now. We got to get 3 pieces of information that the problem gave us. What's one piece of information that this problem gave us? Say again? Okay, so it gives us delta x. What's delta x going to be in this problem? Okay, delta x is going to be 3 meters because it tells us that this diving board is 3 meters high. Now, something that's going to be important in this problem and as we go forward, these are all vector quantities, right? Meaning that they have magnitude, but they also have direction. In this problem, they gave us our reference point and our directional system. They decided that for us. So they said, I'm going to call the diving board the reference point. And then it has this line with the arrow and the x. This really should say positive x this way. So they decided to call downward the positive direction, and that means what? If down is the positive direction, up is negative. Okay? Good with that so far?
Yeah.
So in this case, our displacement isn't just 3, it's actually what? It's actually positive 3. Even though it's going down, we've called the downward direction positive in this problem. So displacement has to be positive 3. Good so far. What else? What else do we know about this kid as he goes from the diving board to the water? Okay, initial velocity is going to be 0, right? The moment that he steps off the edge of the diving board, that very instant, he's not moving. Starts moving almost immediately after that, but the very instant he steps off, not moving just yet. Okay? That's 2. What's the last one? Okay, can't be in this case, all right? Because, well, that depends on what? If we want to know the final velocity of something and we know it starts at 0, we would have to know 2 things. We would have to know how long it was going, but what else would we have to know? Because what causes the velocity to change? Acceleration. Do we know the acceleration?
Yeah.
We do. What is the acceleration in this case?
9.81.
9.81 meters per second squared. Because what's causing the acceleration in this problem? Gravity, right? So an object in free fall has a constant acceleration. It just happens to have a very specific constant acceleration. But acceleration is a vector quantity. Which way is gravity pulling on this kid? Down. So that means that the acceleration in this problem is actually what? Positive 9.81 meters per second squared. Even though it's pulling downward, we've called downward the positive direction. Okay? Now it's just a matter of doing the problem like we've done it before. So you go to your list of kinematic equations and you find out that this equation has the 3 things that we know and the 1 thing we don't know. So you plug in the things that you need, you know, and find out what you're looking for.
Pardon the interruption. One final announcement here. Junior and senior girls, are you ready for some football? We've got sign-up sheets for the annual Powder Puff game to be held at Reed Field on Thursday, November 7th. So if you're interested, please sign up on the sheets posted outside of the main office. We will pull names at random on Thursday, and we'll post the player lists on Thursday. Any football players can sign up to coach on the same signs. Mr. Schindler will be playing. Thanks. Have a great day.
Whoa. That was a joke, Sam. That was a joke. At least I think it was a joke. So. All right. So, Mr. Schindler? Mr. Schindler? Yeah, a little bit. Not very much, though. So. Now, so a couple things before we wrap this up. First, this is how the equation looks in your book. Notice, that is not exactly how I wrote mine. But keep in mind, All they did was substitute in a couple of things that are specific to this problem. It's still the same kinematic equation. It's still the same idea of the relationship between displacement, time, velocity, and acceleration, just updated to fit our situation. So even though it looks different, it's still the same. Okay? We will do some more of these tomorrow, but for tonight, we will do more of those in class tomorrow. For tonight, these problems here down at the bottom are all more conceptual questions about the nature of gravity and the acceleration being constant for all objects. Okay? Yeah, Joe.
Why couldn't you? I know where you got the stuff from.
Yeah.
But if it gave you